I think it's quite interesting. I'll be starting off kind of talking about not necessarily like photonics that will be used for Earth observation, but actually photonics that can help do more Earth observation missions and use more different kind of technologies and instruments. When we're looking at things like thermal imaging cameras and things, they're very power intensive. And I want to show how I'm looking at pushing up the power, the availability of power in space, so that we can use these in the small CubeSats that are pushing Earth observation today. So what space power does, we essentially use photonics all the way from the beginning to the end of our chain, essentially using laser power beaming in order to recharge satellites directly onto their solar panels. So we've got many different applications that we're looking at. So I think more specifically for here, we're looking at LEO constellations and kind of looking into clusters as well, which might be an interesting alternative methodology, which I'll go into a bit later. But also there's anything with a solar panel is what we can beam to. So I'll also walk through a bit of our multi-junction technology, which is a first of a kind, allows us to beam to a solar panel, even if you don't know what it is. And we started to see some really interesting applications as well for lunar missions, especially for things like rescue and emergency missions, where you can see the Japanese SLIM satellite, landed upside down, and then you're basically kind of hoping that the sun will kind of come and recharge it enough to be able to start using it. So we aim to be able to provide these wireless power services and essentially kind of move towards things like asteroid prospecting in the next few decades. So that's really where I get quite interested. So who are we? We manufacture and supply laser-based power banks for spacecraft. That's the best way to think about it. So like your mobile phone, you don't carry around 100 mobile phones with you just because you use them a lot and your battery runs out quickly. You have a recharging system, which is much cheaper and much more efficient. So this is essentially what we're looking at. Why are we looking at constellations of hundreds and thousands of satellites? Essentially, it's because these CubeSats are running for less than 5% of its uptime. So when you're really thinking about the value generated for the asset, the amount of time, sweat, and tears that it takes to launch something into space, we're really trying to help that sustainability angle and really make the most of what we've got up there. And so really the big magic bit is our a technology which allows us to beam to any solar panel. So most of the industry uses triple junction solar cells, and that can complicate things like power beaming quite a bit. And we've developed a system which allows us to beam to anything, to any, especially triple junction or less solar panel, and provide power even if you don't know what your solar panel is. And really what our aim is to launch in 2025 with BAE for a first of a kind mission in order to work with their cluster system. And this is where we see quite a lot of the LEO uses, so low Earth orbit. Sometimes a lot of your instruments do take quite a lot of time to recharge. So if you've got a heavy synthetic aperture radar, for example, or even if you pushed yourself into a thermal imager, you'll find yourself in an operational mode where you're charging your satellite a lot more than you're using the value generating assets. So when you can work in a cluster, let's say you've got satellites flying in formation, you can actually then distribute power as you need it, rather than telling your customer, oh, can you wait 5 more hours for a rescan? Actually, we aim to be able to deliver this in 1 to 2 hours. So this is generally what our system looks like. Call it the SPOC module, the Space Power Optical Charge. And essentially, we've got a bunch of lasers, 2 sets of optics, one for beam transmission and another one for seeing, like a telescope, so that we can see our customer, recognize where it is, and then make sure that we're sending the power to the right satellite. And we're looking at things also for geostationary, looking at things power levels going up to 400 watts. And then, as an aside, I've also done some initial designs for lunar environment, where you're really thinking about lunar dust, the radiation levels that you have there. And it's a weird place with lots of orbital anomalies. So gravity is not actually consistent. And this is kind of what we look at. We're looking first at power banks. So the same module basically breaks out into power banks. So we individually sell that to customers. And then looking forward, actually trying to help minimize the amount of batteries that people need to incorporate into their satellite and enable something like a flyby laser. So, you actually just hook up to our constellation of lasers, and we can then give you constant or ad hoc power charging. And this is our little rover. So that's my little technical demonstrator. It's got its own recharged battery powered by a laser. So it allows me to drive my car wherever I want. The laser's tracking the rover with a automated recognition and tracking system, and make sure that we can see how much power is being delivered back at the control center. So this is our kind of like key kind of like competitive landscape. The real big thing is the backwards compatible technology, and being able to already serve commercial customers. So even if, the big thing is that a lot of the satellites that are up there in the market that's out there today are satellites that were launched, 15, 20 years ago. But really what we want to do is to move into the LEO small sats, where we see a massive value proposition where you can use more of your satellite for things that generate value rather than keeping yourself alive and having your power. So in overall, this is kind of what we look at. We look at our power performance, range performance. Those are the two kind of like defining characteristics of our system. And it's really based around lasers and optics, with the receiver being a photovoltaic. So kind of working closely with suppliers to look at how we can really push this performance as big as possible, looking at, wide spectrum optics, but also kind of like high power lasers with great beam quality. And I can just go into, some of the little technical challenges where we're looking at diode lasers, which have a very elliptical kind of beam, and basically trying to think about how do we shape it so that I'm delivering most or all of that beam to my customer at the end of it. So this is one of the projects that we've got signed up. So this is the launch going into 2025, and kind of really puts it into perspective what the issues are. Sometimes one of their customers will complain to us and say, look, we asked for a scan over this area, and we missed the scan. The ships had moved, and we asked for a rescan. We don't know whether the ship is sinking. There's a smuggling operation. It's been hijacked. And, the custom or the data provider has to tell them, sorry, you've got to wait 5 hours, and it's just too long. So if you've got that charge waiting for you that you can distribute quickly, you enable a lot more performance for your satellites. And we're really working kind of with US Naval Research Labs, who've already demonstrated in-orbit laser power beaming earlier last year. And just kind of gives you an outlook on where we want to push this. So rather than looking at about 1.5 watts being delivered, we're looking at 15 watts being delivered, and going over a kilometer, push the efficiency and make it compatible for everybody. And this is kind of like the overall, where are we and where are we going? This year, we aim to have our minimum viable product build, which allows us to basically, we've scoped out all of the base components, get the space qualification, and really just understand for ourselves, the thermals are going to be the biggest challenge in this product. So how do we ensure that we can keep our lasers on safely for the longest amount of time without degrading its performance and lifetime? That's the quick kind of whistle-stop tour, but then I'm really open to questions and happy to delve into more information.